So we have been looking at how to make alcohols. We have seen that alcohols can be made from alkenes, from the acid catalyzed hydration of alkenes, and also the oxymercuration, demercuration of alkenes, as well as the hydroboration oxidation of alkenes. And don't forget that the acid catalyzed hydration proceeds with a carbocation intermediate, making the reaction very prone to rearrangement. A third method to prepare alcohols is by the reduction of carbonyls. What is a carbonyl? Right now you should know what a carbonyl looks like. This is a carbonyl compound. This is a carbonyl group. Okay. It's a carbonyl group. We have a carbonyl, simply a carbon double bonded to an oxygen. Okay, of course it's going to have that. Now, reductions involve a change in oxidation state. And we know that the oxidation state is a method of electron bookkeeping. Recall how we use formal charge as a method of electron bookkeeping. Each atom is assigned half of the electrons it is sharing with another atom. Okay, so if you are going to consider the formal charge of carbon, carbon usually has 4, but if we break each bond in such a way that each atom is assigned half of the electrons, carbon will have 4. And so the formal charge of carbon there will be, in methanol, will be 0. Okay, now for oxidation states, however, we imagine the bond breaking heterolytically, that the electrons go to the more electronegative atom. The electrons go to the more electronegative atom. So in this case, because carbon is more electronegative than the hydrogens, the electrons in this bond go to the carbon. So that's 1, 2, 3, 4, 5, 6. And all the electrons between the carbon and the oxygen go to the oxygen. So we have a total of 4 electrons for carbon, minus the total number of electrons, which is 6. So that will give the oxidation number to be -2. See? But don't forget, the formal charge here is simply going to be 0. The formal charge here is 0 because it has 4 electrons. Okay, so when you're looking at trying to when you're trying to calculate oxidation numbers, make sure that the more electronegative atom goes with all the 2 electrons that make up the bond. The bonds break heterolytically, while when you are making equivalent, when you are doing formal charges, the bond breaks homolytically. That's a distinct difference. If you look at this, each of the carbon below have 0 formal charges, but they all have different oxidation states. Why is that? If we calculate it, you see that all of them will have different oxidation states. They will have different oxidation states, as you will see shortly. You see that, for instance, this carbon here ordinarily should have 4 electrons, but because the bonds break heterolytically, such that the carbon goes away with 2 electrons, the total number of electrons to the carbon here will be 8 minus 8, so that will be -2. So the oxidation here number is going to be -4. You see? Now, if you look at this one here, we have 1, 2, 3, so 6 electrons. So this is going to be 4 minus 6, and that is, this will be -2. You see? If you look at this one here, you know that it's 4 minus 4, so it's going to be 0. Now if you look at this carbon here, it's going to be 4 minus 1, and that is +3. So the oxidation number here is +3. I'm sorry, the oxidation number here is +2, not +3, because the 2 electrons come from there, so it's going to be +2. Okay, be +2. Well, here you can see again that carbon is 4, and because all the carbon is going to lose all the electrons, so you're going to have 0, and so it's going to be +4. So the oxidation number of carbon here is going to be +4. Now, if you look at the conversion of formic acid to carbon dioxide, we can see it's an oxidation. The reason, again, because look at this here. This is 4 minus 2, which is equal to +2. Because remember, the hydrogen gives the 2 electrons to the carbon. That's the 2 electrons here, right? And then here, if you notice what has happened, all the electrons are lost to the oxygen. So carbon goes away with nothing. And so you have 4 minus 0, and that is +2. +4, I'm sorry. 4 minus 0, that's +2. So +4, I'm sorry. So you can see that this is going to be an oxidation. Oxidation because it goes from +2 to +4. Now, if you look on the other hand here, you have a total of 4 electrons for carbon, and each of them goes, the hydrogens give 2 electrons each. So that's -4, that is 0. But here, the hydrogens give 2 electrons each, that's 6 electrons total. So that's 4 minus 6, and this is -2. So carbon goes from 0 to -2, and you can see this is going to be a reduction. Okay? So these are things for you to watch for. Okay? Now, what of formaldehyde? Formaldehyde to methanol, we have already talked about it. Now, the reduction of carbonate requires a reducing agent. Okay? Requires a reducing agent. And the reducing agent is usually oxidized. Right? Because for the agent to be reducing, it must lose electrons. That means it's been oxidized. If you were to design a reducing agent, what would be necessary? Of course, if you have like a hydride, that would be a great reducing agent. Acids cannot be reducing agents because the electron doesn't have its, this electron has been lost. This is a proton. It has been stripped of its electron. It doesn't have an electron, so it can't be a reducing agent. For it to be a reducing agent, it needs to have an electron source. Now, there are three reducing agents that we need to know about. We have already seen how catalyzed hydrogenation can reduce alkenes. It will also work for carbonates, but the problem with this is not selective. This is not a selective reaction. You can carry out the reduction of a carbonyl to an alcohol, in this case a secondary alcohol, right, using hydrogen over platinum, palladium, or nickel. Okay, but the downside of this method is that you have to use forceful conditions, high temperatures, and high pressure. See, and so you need a reagent that is more mild, right, and will be able to do the job with better selectivity. And so chemists have turned to hydrides. There are two hydrides I'm going to introduce to you. The very first is sodium borohydride. Sodium borohydride will reduce a ketone to the corresponding secondary alcohol. So this is a secondary alcohol, right? And how it does it is by a nucleophilic attack. In the first step, sodium borohydride delivers a hydride, as you can see, to the carbonyl group, and then you have a proton transfer. The resulting alkoxide is then protonated to form the alcohol. So it takes the ketone, as you can see here, to give the secondary alcohol. That's for sodium borohydride. Okay. Now we also have lithium aluminum hydride. This is a much more harsh reagent. It will take an aldehyde to the corresponding primary alcohol. Okay, just like sodium borohydride, right? And the way it does it is by delivering a hydride, right? And eventually you get your product. It will also take a secondary, a ketone, to the corresponding secondary alcohol. Okay. Now note that the lithium aluminum hydride is significantly more reactive than the sodium borohydride, and the lithium aluminum hydride, LAH by the way, reacts violently with water. The reason because it has a more polar aluminum hydrogen bond. The bond is more polar, and so the reaction is more violent. Okay. Now sodium borohydride will take a ketone to the corresponding secondary alcohol. Lithium aluminum hydride will take the aldehyde to the corresponding primary alcohol. Now, lithium aluminum hydride can be used with water because even though it reacts with water, the thing is you have to use an excess. So when you use an excess, then you are sure that it will be able to carry out the reduction. Now, the hydride delivery agents will somewhat selectively reduce carbonyl compounds. Okay, as you can see here, sodium borohydride as well as lithium aluminum hydride will take the ketone to the corresponding second degree alcohol, right? But notice that it will not touch the alkene. It leaves the alkene alone. The alkene is still intact. See, the alkene is untouched. You see, it's untouched. It's untouched. But in the case if you use hydrogen over palladium or platinum or nickel, you find that it will reduce the alkene as well. So here the alkene is reduced, meaning that this reagent is less selective. See, this is a less selective reagent. This is more selective. So selectivity is very important to us as chemists. Now, the reactivity of hydride delivery agents can be fine-tuned by using derivatives with varying RH groups. So you can simply replace some of the hydrogens with R groups or alkyl groups, or other groups like alkoxide, cyano groups, or sterically hindered groups. Now, okay, an example of that is dibutyl aluminum hydride, or DBA. See, so dibutyl aluminum, there are two butyl groups, aluminum hydride, DBA. Okay, and DBA will take an acid chloride. So when you have an acid chloride, you take it to give the aldehyde. See, to reduce it by simply delivering the hydride. That's something that you are going to see eventually. The lithium aluminum hydride is strong enough to reduce esters and carboxylic acid, whereas sodium borohydride is generally not. So this is a difference. Note this, okay? Lithium aluminum hydride is strong enough to reduce esters and carboxylic acids, while sodium borohydride is generally not. Okay, and so to reduce esters, you just need an excess of lithium aluminum hydride, and then you add water later for the hydrolysis. Notice that the water comes later. The water is not mixed with the lithium aluminum hydride in the first step. It's only in the last step, which is the hydrolysis. Okay, now to reduce the ester, two hydride equivalents are needed, as you can see here. The first delivers hydride is used to reduce it to the aldehyde, and then the second, so this is the first hydride, reduces to the aldehyde, and then the second hydride reduces it to the alcohol. Okay, this reduces to the primary alcohol. And you can see that the proton transfer step is reversible. Now, let's predict the pros for the following reactions. Of course, we know that sodium borohydride will not touch an ester. This is an ester. It will not touch an ester. It will only reduce this. See? It can't reduce an ester. Right? So we expect that the ester will be intact. So ester here is intact. See? Only ketone is reduced. Okay, but with lithium aluminum hydride, notice that both ester and ketone have been reduced. You see, reduced. So you can see that the sodium borohydride is more selective. It's more selective because it doesn't touch the ester. Okay, so that's something you need to know, the difference between using sodium borohydride and lithium aluminum hydride.